Okay, hello, my name is Ben Intoy, and today I would like to present the effects of a spatial diffusion on a model of prebiotic evolution, work that I'm doing with my postdoctoral advisor, Professor Halley, and collaborator Aaron Weinveen, all at the University of Minnesota, Twin Cities. So some quick motivation. A protein first origin of life model can resolve Eigen's paradox, which is the low probability of generating randomly constructing a starter naked gene. And we assume an initiating event is the formation of a network of interacting molecules, assumed to be polymers, but not necessarily proteins. We have no genome, and we assume that it comes much later. And unlike previous similar models, we assume here that a necessary condition for a prebiotic chemical system is that it be a stationary state out of equilibrium. So real quickly, would like to go over a Kaufman-like binary polymer model. So our reactions are ligation incision of binary polymers. So here I have just an example reaction. So 0, 1, 0 plus 1, 0. Catalyzed by polymer 1, 1, gets ligated into 0, 1, 0, 1, 0. And then the opposite direction is scission. And so to make our network, given a maximum polymer length value, which we call Lmax, which is a parameter in our model, we go through each possible reaction of the form A plus B, goes to AB catalyzed by C, and included in the network with probability P, which is another parameter in a model. And the chemical species in the network form an autocatalytic set, which will be elaborated on in Cole Mathis's talk preceding mine. And so for dynamics, we come with our chemical network that we just made, we combine it with reaction rates to generate an artificial chemistry, then stochastically simulate the following master differential equation. So NL is basically the number of polymers of species L, and all these terms represent the reaction rates of ligation and scission. And the parameters in our model are P, L max, the number of food particles, and the maximum number of particles that we can have in our system. So now I'd like to just give a brief general structure of what we did. So for these different P values, we generate multiple networks, typically 10,000, and check if they're viable. And all viable means is that it's possible to go from the food set all the way to a molecule of length L max, given the reactions in the network. And then we do multiple dynamical simulations with random initial conditions using a given viable network combined with reaction rates until a steady state is reached. So here, I have the viable networks labeled in blue, and then the non-viable networks labeled in red. And so for each viable network, we we do dynamic runs, and depending on whether or not they're in then we count basically after we run until steady state is reached, we count the number of lifelike steady states by checking if the system's out of equilibrium. So basically with these runs, we just check if they're out of equilibrium or not. And with this, we now have a measurement for the probability of forming a lifelike state for a given value of P. So I would like to go over where Kaufman and our group differ. So when Kaufman simulated these models, he saw population growth with increasing P. So here I have a little example where red is the population as a function of time, simulation time, and we see that increases. However, the system might be growing, but it might be in chemical equilibrium. So here I have these two runs with the same P value in artificial chemistry, and also the same chemical network. And this one, although it's growing, reaches a chemical equilibrium. And here in the green line, I have a measure of what we mean by chemical equilibrium, where 1 is where it means the system is chemically equilibrated, and 0 is the system is not chemically equilibrated. We see that this one reaches chemical equilibrium, whereas this one grows to a maximum but stays out of chemical equilibrium and is kinetically trapped in a non-equilibrium steady state, which we postulate to be a necessary condition for life. And this non-equilibrium constraint reduces the probability of lifelike systems at large P, giving a maximum value at a small value P. So here I have a figure from a previously published paper where I have the probability of forming a lifelike state on the y-axis and the P value on the x-axis. And we see there's a maximum around the P value, or P 0.005. So now I'd like to explain, how close a system is to chemical equilibrium. We use entropy. So we coarse grain by polymer length. So NL is the number of polymers of length L, and we have a distribution of these for all the different lengths. And given the macro state, the number of possible configurations is given as W, given as this formula. And we say the entropy is defined as S, which is equal to KB log W. And this is a thermodynamic, more of a thermodynamic entropy rather than information entropy. And we say chemical equilibrium is reached when this entropy is maximized, which we call SEQ, with the constraint that there are n total molecules in the system. And we simulate until a steady state and consider it lifelike if the entropy is less than alpha times SEQ, where alpha is a parameter in our model that's between 0 and 1. So now I'd like to go into why we want to extend this to diffusion through space, some motivations. So we're wondering how might spatial structure affect prebiotic evolution, and so for some motivations, wondering if the non-equilibrium states of the model without diffusion survive interaction with the environment through diffusion. So this gets into the compartmentalization that Tessa was going over earlier. And we're also wondering if there are collective effects which might suggest the beginnings of multicellularity. So this sort of goes into complexity. So now I'd like to go over our spatially extended model. We study 64 sites arranged as an 8x8 2D periodic lattice. And here I have a little sketch where these squares represent sites. And inside each site, there's the same artificial chemistry. And molecules are allowed to diffuse from site to site at a rate parameterized by eta. And due to computational limitations, we set L max equal to 6. So now that we have a space in our model, not only can we chemically equilibrate, we can diffusively equilibrate. So I just wanted to go over how the system can be partially and completely equilibrated. So now that we have space in the model, our polymer length distribution also depends on space, which we call I, and we label that point P in this macro state space with the 384 dimensions. And like I said before, it can be diffusively equilibrated, which we call the diffusively dead and locally alive. And that just means all the particles of length L are evenly distributed across the lattice and has a distribution as so. And we label it PD on this macro space. And the system can also be chemically equilibrated at each site, which we call diffusively alive, locally dead. And that just, we label that as PC on this macro space. The system can also be chemically and diffusively equilibrated, which we call totally equilibrated, and we just call it dead. And if it is not diffusively or chemically equilibrated, we call it diffusively alive and locally alive. And so how to check how far the system is away from these different partial equilibria, we basically take the Euclidean distance between the distributions. So we have the distributions of the system point and what it should be if it's partially, in this case, partially diffusively equilibrated. And we just basically take Euclidean distance. We call that RD, the distance between the system point and the point at which it's diffusively equilibrated, and RC, the distance between the system point and the point at which it's chemically equilibrated at each site. So now I just want to show an example of results for these two distances in a simulated non-equilibrium steady states. So here's I really need to look at this. So this is a scatter plot with about 20,000 runs, where the color of the point denotes the entropy ratio. And note that we already require that the entropy ratio be less than 0.6. And these two normalized distances that I defined earlier. So now with the scatter plot, we can start labeling these steady states, depending on how far they are from either being diffusively or chemically equilibrated. So if the system is diffusively equilibrated, so it's close to its diffusively equilibrated point, or far away from its chemically equilibrated point, we call it diffusively dead, locally alive. So all the points in here are considered DDLA. And if system is chemically equilibrated but far away from its diffusively equilibrated point, we call the system diffusively alive, locally dead, and which will encompass all the points in this compartment. And then if the system is both far away from being chemically and diffusively equilibrated, we say it's diffusively alive and locally alive. And it would be all the points in this compartment. So now with this, we can start forming probabilities. So here I have the probabilities of forming these three states, which are the height axis on all these plots as a function of P and eta. So P is the width axis, and the eta is the depth axis on all these plots. And some things to note is the probability of forming these DALD states is very low compared to the others, and that we get the similar results with the single site model for the DDLA states. We're starting from P equal to 0 and increasing P, we see that the probability of forming a lifelike state goes up and comes back down. However, that's not the case when we look at these diffusely and locally alive states, where the probability of forming lifelike states seems to taper off, even at there seems to be still lifelike states even at a high p-value. So looking at these states, we see that they display these cancer-like explosions. So here I have the entropy ratio and this is for a single run. I have the entropy ratio as a function of time, and we see that it starts off in some metastable state where we don't consider it alive because its entropy ratio is greater than 0.6. But after some time, all of a sudden, the system goes down into another metastable state where it is now considered alive since its entropy ratio is less than 0.6. So looking at a screenshot before and after this jump, we see that before the jump that there are less than 100 non-food particles per site. But after the jump, at this red X, we see that all of a sudden the number of food particles on one site goes up to 900. So this would be considered to be totally diffusely out of equilibrium since all the particles are mostly on one site. And note that this is for a very, very low value of eta. So if we increase eta, we see a collective effect where this explosion spreads. So here I have the same the ratio of the entropies as a function of time. And we see like before, it starts off in some type of metastable state. And then right before this cliff, we see one site explode. And then that explosion will spread to the other sites before it reaches a minimum. And then we see the entropy ratio go up to 1 since the system is starting to be totally equilibrated. So just some conclusions. I've stated most of this before. There were, we counted likelihood as a function of P and eta. These lifelike states characterized as DALA, DALD, and DDLA. And we see that these DDLA the DDLA states closely reproduce the states in an earlier single site model. These DALD lifelike states are rare. DALA exhibit these explosive-like growth. And then for some future work, we'd like to explore some other forms of spatial inhomogeneity, which I have listed here. Thank you.
We have time for some questions.
Hi, very interesting talk. I am wondering about the polymers. Which polymers do you think are possible on Earth? Like, since you did the...
Well, that's the thing. We didn't have that in mind. Yeah, because we wanted to be as abstract as possible.
Yeah.
So we didn't want to have any like terrestrial life-like bias in our model. So that's why we have a very simple model. But we don't. There are a couple applications, but I can't recall them off the top of my head. Sorry.
As a note to that, as a note to that question, there are at least a couple labs where people have looked at these types of systems in RNA chemistry as well as like peptide chemistry.
Mm-hmm.
So it's
not except the RNA. I was wondering, is there other possible polymers? Thank you.
Any other questions? Okay, next we are going to be hearing from Cole Mathis, appropriately enough.